Welcome students in the new chapter which is the current electricity of class 12 CBSE board students in the physics. So let's begin with the chapter current electricity with short introduction of electric current. So what is a current? An electric current is the flow of a charge in the electric circuit. This charge is often carried by moving electrons in the wire. The mean of a charge is The mean of a charge, it is the inherent property of a matter. Inherent property. That means it is the intrinsic property of the substance. So, and when these charges are moving, so current will be induced. Now the things will be like that. Flow of electron. This is a charge which have negative property. And if I'm just taking a proton or a positron, so this will be have a positive in the nature. It can also be carried in electrolyte by both ions and electrons such as in the plasma. So the flow of a charged particle, that is a lightning, is an example of a charge flow from the cloud to the earth through the atmosphere, sometime with disaster results. So this is also an example of a lightning. So they have a negative ion, there is a positive ions for that. Flow of water in a river is called water current, as you can see over there. And flow of a heat in a conductor we are saying as a thermal conductor. As you can see, the temperature is changing when this oil, this rod is heat up. So there will be flow of a charges will be start to take place. Because of its sake, we can say that there will be a transient current flowing in the circuit. Next, flow of the charges in the current we will call as electric current. Strength of electric current. So, the rate of flow of charge through any cross section of a conductor is called the strength of electric current. If delta Q is the net charge through any cross section of conductor in delta T time, then average current I is given by average current I is equals to delta Q by delta T. Electric current is a fundamental scalar quantity and the dimensional formula I or A. SI unit ampere. Definition: the current through a conductor is said to be 1 ampere if the charge of 1 coulomb flows through any cross section in 1 second. So I is equals to Q by T. If Q is equals to 1 coulomb and T is equals to 1 second, then I is equals to 1 ampere. If 6.025 10 to the power 18 electrons flows across the conductor in a 1 second, the strength of the current flowing across the conductor is of 1 ampere. Knowledge plus we have the direction of a conventional current is the direction of flow of the positive charge or opposite to the direction of flow of the negative charge. Even though electric current has a both magnitude and direction, it isn't taken as a scalar quantity. The reason is here that it does not follows or obeys the law of vector addition. In metals, current flows due to the free electrons. So firstly, I just want to elaborate what is the actually the law of vector addition. So as you can see, if the current is a pass from here 2 ampere, if the current is again pass from here, this is a current which is a 1 ampere. So the upcoming or the total current which is elaborating here, this will be 6 ampere. But according to the vector addition, if this will be in a 2 ampere and the direction of another current we have or another directive quantity if you have, so the resultant will be minus 1 ampere. Like this kind of effect we can see in the vector addition, which can't be happen in the case of a current. So in a semiconductor, charge carries in both electron and holes, and in electrolyte, the charge carries are both positive and negative ions. The instantaneous current is defined by this equation, like I is equals to limit delta t tends to 0 delta q by delta t or dq by dt. So this is the measured here, the diagram I is equals to delta q by delta t measured here. So if the current is varying with time, then the charge flowing in a time interval t1 or t2 is q is equals to t1 to t2 dt is equals to area under the curve IT graph. If n particles each of a charge q pass through a given cross section in a time t, then average current I is equals to nq by t. The average current associated with revolving charges I is equals to q by t is equals to fq, or f is equals to omega by 2 pi. We know omega by 2 pi is equals to frequency. So we just put all these value over there. V by 2 pi r is equals to, again, V is equals to L by mr, or L is equals to mvr. We know this is a moment, angular moment. So during the circular motion, angular momentum remains conserved. So we will use this term here over there and get the result. If f the frequency, so frequency of revolution is in hertz. Omega is the angular frequency, so the unit is radian per second. And L is equals to mvr in a angular momentum. R is the radius of the circular path. If in a discharge tube N1 proton are moving in the left to right in t second and N2 electron are moving simultaneously from right to left in t second, then the net current in the any cross-sectional tube is E is equals to magnitude of a charge of electron and proton. That means E is equals to N1 plus N2 times E divided by T. Classification of a current. So current have two types, steady current and non-steady current. This is a steady current. Those current are not changing with respect to time and their surrounding, which we will call as steady current, like this. Non-steady. Non-steady means the current which is continuously varying with respect to time. This is called as non-steady current. So as we can see here, the current will be same, like a 5 ampere in a 10 second, 5 ampere in 20 second. So this will be called a steady current. But here, as you can see, there's some fluctuations or pulses are made in here. That's why this is a non-steady current, which is as say as a AC current. Now, the current electricity, we will see about the DC. So materials, conductors, insulator. Conductors allow the flow of electric current. Insulator does not allow the flow of electric current. What is the SI unit of electric current? We have these options. Yes, so the correct answer is ampere. How many number of electrons pass through a conductor when 1 ampere current passes through it in 1 second? These options are here. Yes, the correct answer is option B, according to this formula. Next question we have, which of these following is a fundamental quantity? The correct answer for this question is electric current. Drift velocity. So, random motion of electrons in a conductor when no potential difference is applied across the conductor. Like we have these electrons. So, if we just take in a reference of I'm just taking a 50 electrons are there and 50 electrons are there. So, net flow of a charge will be 0 when the potential difference applied across the conductor. So, they will be transfer the energies among them in this direction. Drift velocity of an electron in a conductor. So this is the diagram of a drift velocity. As you can see there, this is a negative charge, which is the electron are moving there in the opposite direction of the current. So electric current is due to the flow of electrons in the conductor. How does the electrons move in a conductor in the absence of electric field? At any temperature, the free electrons are randomly moving in all the possible directions. How does net rate of flow of electrons at any point in a conductor in an absence of electric field move? The rate of flow of electrons from left to right at a point is equals to the rate from the right to left, so that the net rate of flow of electrons at that point is zero. In the absence of electric field, how do electrons accelerate in a conductor in the presence of electric field? What do you mean by drift velocity of electron? So an electric field is set up at every point in a conductor. When it is connected by a battery, this field exerts a force on electrons as they move, undergo frequent collision with the atom. Thereby, they acquire a constant speed in the direction opposite to the field. This velocity is called drift velocity, which is of the order 10 to the power minus 3 meter per second. Thus, there is a net flow of a charge inside the conductor. The collision between the electrons and the atom ion of the conductor are inelastic, and there is a net transfer of energy. The average time interval between two successive collisions is called relaxation time, which is represented by tau. So drift velocity Vd is equals to minus E tau by L, where V is equals to 80. So here negative sign indicates that electron drift opposite to the applied electric field. Point must remember, when electrons are drifted in the conductor, they will have a net average velocity and zero average acceleration. In the absence of external electric field, there will be no current in the conductor. Electric current density J. So current density is defined as the current per unit area. That is a J is equals to I by A. The magnitude of a current density is the amount of a charge flowing per unit cross-sectional area per second is a vector quantity. If E is the magnitude of a uniform electric field in the conductor whose length is L, then the potential difference V across its end is E by EL. So EL is equals to J rho L and E is equals to J rho. In the above relation, for magnitude, E and J can be indeed be cast in the vector form. The current density, which have definite as a current to unit area normal to the current, is also directed along E. E is equals to J rho, J is equals to sigma I, where rho, sigma is equals to 1 by rho is called conductivity. SI unit, dimensional formula. So SI unit will be ampere per meter square. SI formula IL to the power minus 2. Relation between electric current and drift velocity. Consider a current conductor of a length L and a uniform area of a cross-section A. Volume of the conductor is V is equals to AL, as you can see over there, this formula. So if N is the number of free electrons per unit volume of the conductor, then total number of free electrons N in the conductor is N is equals to NAL. Hence the net charge of all the free electrons in the conductor is NAL times C. Let's constant potential difference V is applied across the end of the battery. Electric field across the conductor E is equals to V by L. Due to this field, the free electrons in the conductor moves with a drift velocity Vd towards left side. Time taken by free electrons across the conductor T. So T is equals to L by Vd. I'll just put all these value and get the formula of I, which is I is equals to NEA Vd. And if I just put the value of Vd, so this will be result come. current density in terms of drift velocity. J is equals to I by A is equals to NeVd. Mobility mu. Mobility mu of a charge carrier electrons is defined as the average drift velocity of electron, that is the mu is equals to drift velocity per unit electric field. Now the types of a collision takes place between the electrons and the atoms or ion in the conductor is inelastic collision. The drift velocity of an electron in copper conductor of a cross section 5 to the power minus 6 meter square is 1.5 to the power minus 6 meter per second. If the current is a 10 ampere, find the number of electrons using per unit volume. We have these formula and these equations of the number. The first option is the correct option. What is the relation between drift velocity and electron and electric current? V is equals to I by NeAe. So we have these options. The correct option for this question is option first. So this is all about for today's class. Thank you so much for watching this video.